All right, let's dive right in. Today, we're playing detective, cracking a modern engineering mystery. Why do our perfectly good apps suddenly just collapse under pressure? We're going from Flask to Quart to solve what I'm calling the concurrency crisis. So picture this. You've built this beautiful Flask app. It's elegant, it's simple, it works. It's a masterpiece. But then, the moment you throw real-time traffic at it, I'm talking WebRTC signaling, WebSockets, that kind of stuff, it just hits a brick wall. It crumbles. So why? Why does this masterpiece fall apart under the very load it was meant to handle? That's the mystery we are solving today.
And this brings us right to our first piece of evidence in the case of the crashing server, what we're calling the concurrency crisis. The scene of the crime? Your server. The victim? Your poor application, buckling under the pressure of all those real-time connections.
Now, at the heart of this whole thing is a classic computer science challenge. You might have heard of it. It's called the C10k Problem. It sounds super technical, but it's really just the challenge of getting a single server to handle 10,000 connections all at the same time. And here's the thing. Traditional servers, like Flask running on WSGI, they were just never ever designed for this kind of a world of persistent, long-lived connections. So who's our prime suspect in all this? It's the Web Server Gateway Interface, or WSGI. See, in the old synchronous world, one worker process handles exactly one request at a time. So when a long-lived WebSocket connects, it grabs a worker and just sits on it, forever. If you want to handle more users, you have to spin up more workers, which means more threads, and pretty soon your memory usage just goes through the roof. And here's the really crazy part. Your server ends up spending almost all of its energy just keeping these idle threads alive instead of actually processing data. And this is the perfect way to think about it. Imagine your server is a highway. With WSGI, each connection gets its very own lane. But the second it has to wait for data, the car just stops, right there, in the middle of the lane. So what happens when all the lanes are blocked? Well, if you only have 16 lanes, that 17th car, your 17th user, is just stuck in a massive traffic jam, staring at a loading spinner. That, my friends, is head-of-line blocking, and it's what grinds your entire application to a screeching halt.
So, are you following the clues so far? If you're ready to see how we crack this case wide open, do me a favor. Hit that subscribe button and comment present down below to let me know you're on the investigation with us.
All right, let's get back to it. Now for the breakthrough. See, the solution isn't about building a bigger highway with more lanes. No, it's about fundamentally rethinking how the traffic flows in the first place. This is the async paradigm shift. And this right here is the absolute core difference. On the left, with WSGI, you've got the operating system desperately trying to juggle thousands of really resource-heavy threads. But on the right, with ASGI, the application itself takes control. It cooperatively yields control whenever it's waiting for something, like a database query to come back. This means nothing ever blocks the main road. The result? Incredibly low memory overhead, and a much smarter way to handle waiting. So the crucial point is this. The solution is not to just throw more hardware and more threads at the problem. The solution is a smarter system. And the hero of this whole story is the Asyncio event loop. It's a single, highly efficient process that can juggle thousands upon thousands of connections because it never ever just sits around waiting. And the evidence is, well, it's staggering. To handle 1,000 concurrent users, a threaded Flask app might eat up over 4 gigabytes of RAM. The same exact workload on an async architecture? Less than 500 megabytes. That's not just an improvement, that's a revolutionary drop in how many resources you need. Okay, so we get the theory, but how do we actually apply it without having to rewrite our entire application from the ground up? Let's bring in the right tool for the job, Quart, the drop-in solution for Flask developers. The best way to think about Quart is like an engine swap for your favorite car. You get to keep the familiar, beloved API of Flask, the routing, the templates, all the extensions you know, but you're swapping out that old synchronous WSGI engine and dropping in the high-performance, non-blocking ASGI and Asyncio engine. And this just brilliantly illustrates how seamless the transition can actually be. I mean, look at the code. You change your import from Flask to Quart, you change your function definitions from def to async def, and then you just add the await keyword for any operation that involves waiting. That's pretty much it. The core logic and structure of your app, they stay intact. Okay, but does it actually work? Talk is cheap. Let's look at the hard evidence. This is performance under pressure.
The results here, they're not just better, they're in a completely different league. A standard Flask and Unicorn setup, it really starts to struggle, and it taps out around 1,000 concurrent connections. But Quart, running on a modern ASGI server like Unicorn, it doesn't even break a sweat as it flies past 10,000. And it's not just about how many users can connect, it's about how fast the server can respond to them. We're talking about up to a 9-fold improvement in raw throughput, that's requests per second. This means your application isn't just more stable, it is dramatically faster for every single user. And I think this quote from the source material just says it all perfectly. It's the same Python you love, just ready for the real-time era. You don't have to abandon your favorite language or your skills to get this next-generation performance. Okay, so you're convinced. But how do you actually do it? Let's move to the final part of our investigation, the surgical migration. This is your action plan.
Here's the playbook. Step 1, swap that import. Easy. Step 2, refactor your routes to use async and await. This is the core of the work. Now, step 3 is critical. This is the big pitfall. You must replace any blocking libraries with their async native versions. A single synchronous call can block the entire server. And finally, for any heavy CPU work like cryptography, you offload it to a separate thread so it doesn't stall your main event loop.
So the verdict is in. The benefits of making this switch are clear, and they are massive. You can handle a huge number of concurrent users, your latency stays low and predictable even under extreme load, and you can achieve all this with a fraction of the servers, which will dramatically cut your infrastructure costs.
So, if this investigation helped you crack the case of your own concurrency crisis, please share it with your team. And if you're ready to take your own applications to the next level of scale and performance, go ahead and give this explainer a like. Thanks for watching.